Okay, hi everyone. My name is Emily. I'm your SI, and I totally messed up the Zoom stuff for today's meeting. Today is August 31st, so I'm recording this for you guys that wanted to join virtually but couldn't because I messed up. But I do have it fixed, so on Wednesday, September 2nd, you will be able to go to my website, click on that link that says join with this link, and it'll take you to the Zoom meeting. It'll be live. You can interact. You can ask questions. Yeah, so that's all fixed now. Okay. So I'm going to actually go ahead and introduce myself a little further. So my name is Emily. I'm a junior here at Tarleton. This is my second year SIing for chemistry, and my second semester being an SI for Miss Adams. So I also took her when I took chemistry, so I'm pretty familiar with her exam setups and the types of questions she asks. You can always text me through Remind or email me. My email is on my website. So those are all modes where you can contact me if you have a question, or if you're watching a recording or something and you are like, what the heck, that doesn't make any sense. Always feel free to reach out. I'll do everything I can to help you. So about me, I totally got off track. I study medical laboratory science. So I want to be a medical laboratory scientist. And if you're in chemistry, it's likely that you're doing something that focuses on health, the body or an animal's body or something. And chemistry is super essential to that. I know everyone likes to tell horror stories about chemistry, and it's the hardest class they've ever taken. And it's definitely difficult for some, but I'm here to help you through it. It's doable. You got accepted to the school. They clearly think you can succeed, and you have the ability to succeed, and I'm here to help you do that. Okay, so I won't keep yapping. So I'm going to go ahead and work on my laptop and share my screen with you. So let me pull up the worksheet. On Wednesday, I'll do more math from chapter 1, doing more dimensional analysis, things like that. And I'll also start going into chapter 2, which we've just started. Okay. So starting with the first question, matter is defined as anything that, and I'm going to go ahead and pause in between these questions so you have time to think about it, and I don't like say the question and then just start typing out the answer and you don't really have to think. So there are two things that are required for something to be defined as matter. So think about what those things are. What does it mean to have matter? What qualities do you have to have? So here, matter is defined as anything that has mass and takes up space. So that should kind of sound familiar to you because we went over in class. So next, just sort of looking over question number 2, the way that it's worded, what do you think I'm asking about? If you saw this question, there's no other background, there's just this on a quiz, what would your mind go to? Something that has definite volume but not shape, definite shape and volume, or no definite shape or definite volume? What are these qualities describing that we've talked about so far? Okay, so this is talking about states of matter. So think about what state of matter is going to have definite volume but not definite shape. So what's going to have a set amount but not really shape? The shape is very fluid. I don't want to use that word because it's fluid, it's liquids. So liquids have a definite volume, but not definite shape. So there's a set amount of liquid that you can have, and it'll fill whatever container you want. So I have this spray bottle that I use to mist my plants, and as definite volume, this is a 2 fluid ounce spray bottle. It's going to be 2 ounces no matter what I put this in. But right now it's conforming to the shape of this bottle, whereas if I poured it into this glass, it's going to take on a different shape down in here. Or if I put it in this bottle, it's going to take on a totally different shape than it does in these two. So that's defining a liquid. So what state of matter is going to have a definite shape and a definite volume? It's going to be a solid. Solids have definite shape and volume. So let's take chapstick for an example. There's this tube of chapstick. It fits perfectly in this container. Well, if I took it out and I wanted to like shove it through here, it may not fit because its shape is fixed. There's nothing I can do to change it, which isn't totally true for chapstick. You can like melt it, but then it would become a liquid. So in its solid state, this is its shape, and that's all it is, and there's nothing you can do about it while it's a solid. Okay. And so finally, no definite shape or volume is going to be gases. So this container here, there's gas in here. There's air in this thing. And when I close it, whatever air is in there is conforming to this shape. It's filling all of it up. So if I have like a really concentrated gas in here, it's going to fill up this area. But when I flip open the lid and it goes and it diffuses throughout the room, now whatever concentrated gas was in here is taking up all of the space in my room. It wants to be as far away from other gas particles as it can possibly be. So what is the difference between weight and mass? And this kind of goes back to question number 1. So matter is anything that has mass, but what exactly is mass? So mass is the amount of matter in an object. So mass and matter are very intertwined. So mass, amount of matter in an object. Now, what about weight? We use weight a lot to talk about, well, everything. We talk about everything and how much it weighs. When a lot of times we mean how much mass does it have? What's the mass of the object? So the definition of weight is very like physicsy. It reminds me of a lot of physics because we're talking about force. It's going to be the force of gravity on an object. How much gravity is pressing down on this? Okay. So next is define the law of conservation of mass, and I worded this weird. Define the importance of the law of conservation of mass. Why is this so important in chemistry? Those are the same things. I asked the same question twice. But really what I want you to do is define the law of conservation of mass, and then think about why does that matter in chemistry? Why is this such a big deal? So think about it for a second. So the law of conservation of mass is that matter cannot be created or destroyed. So why does this matter so much in chemistry? And particularly, I want you to think about your labs, types of lab things you'll be doing. So if matter can't be created or destroyed, and we take two reactants and we put them together and it goes through a reaction and we get product. What does that tell you? So it means that however much you have on the reactant side, you must have on the product side. Something doesn't just disappear, or nothing just randomly appears in your chemical equation or in your reaction in lab. Sometimes the mass will change. A lot of that comes from doing reactions where you lose energy as heat. That happens a lot. So what this means in chemistry, the reason this is so important is in chemical reactions / equations, you must have equal matter. Ooh. Equal matter on the product and reactant side. And that's why it's important. And pretty soon we'll get into balancing equations, which I think is fun. I enjoy it. And that's where this law really comes into play, and you really have to remember it and think about it. So list an order of organization from simplest to most complex. So what I mean here is, well, I don't know how else to break this down. The simplest thing listed to the most complex, and I'll give you a second to like think about it. Okay, I'm gonna go ahead because it's weird to just sit here. So if you still want to think about it, you don't want the answer just thrown at you right now, go ahead and pause the video, think about it for a bit, and then play it whenever you're ready. So the simplest item here is going to be subatomic particles, because these are the protons, neutrons, electrons, everything that makes an atom an atom. So the next up is going to be an atom. So one thing that I really want to hit on here when we're talking about atoms and subatomic particles, an atom is the smallest unit that retains the properties, the chemical and physical properties of an element. So if you have one atom of aluminum, it's going to have those physical and chemical properties. But the second you go down that level of organization, you go into protons, neutrons, electrons. Protons, neutrons, and electrons don't hold any elemental properties. It's when they combine just right to make an atom. And so lastly is going to be a compound, and this is when you have two or more atoms. So I'm going to ask you a question, pause, think about it, play when you got your answer. What is oxygen? The oxygen that we breathe. What would you class that as? Okay, so it's a compound. So if you didn't know, the oxygen that we breathe is O2. It has this little subscript, and that little subscript there denotes that there are two oxygen atoms bonded to each other. And we'll go more into bonding and why it has to be bonded and all of that, and why it can't just be a single oxygen atom. We'll get into that a bit later. But for now, all you have to know is that it's O2, and that makes it a compound. So even if it's two of the same atom, if they're bonded together, that's a compound. So other examples of compounds are like carbon dioxide, table salt, sodium chloride. Those are all compounds. Whereas like an atom, you could even put that this is like a pure element. So if you have an atom of aluminum, it's an atom, it's an element. Okay, so question number 6, what is a mixture and what types of mixtures are there? So give you a second to think about it. What defines a mixture? What makes something a mixture? So a mixture is two or more types of matter that can be separated. So what types of mixtures are there? There are two different types that will come up again and again that are very important to know. So the two different types of mixtures, one of them is homogeneous mixtures. And they can also be called solutions. And you're going to be making a lot of solutions, naming solutions. Solutions are a big thing. And so what this means is that it's uniform throughout. You look at it and you can't see the different pieces. It has pretty uniform composition. So one thing that we talk about a lot is aqueous solutions, and aqueous means dissolved in water. That's all it means. You can think aqueous, aqua, water. So a good example of this is salt water. That's an aqueous solution. It's a homogeneous mixture. Same thing, those mean the exact same thing. So you take the salt water. When you look at salt water, you can't really tell that there's salt in it, unless it's like super like crazy concentrated and there's some like floating at the bottom. But then that's not really homogeneous. So you have a perfect solution of salt water where all the salt is dissolved in it. Now, if you grab that, you think it's water and you take a sip of it because it just looks like water. But if you put it in a pot, you boil it down, you're going to be, after a while, all of the water will evaporate and you'll be left with the salt crystals all around the pan or pot. The second type is a heterogeneous mixture. And these are classified because these can be identified because they do not have uniform composition. So a good example of this is like chicken noodle soup. So like if I had a big deal of chicken noodle soup and I ladled some into a bowl for me and ladled some into a bowl for you, well, maybe I have more broth, maybe you have more chicken, maybe you have more noodles, maybe I have more vegetables. It's not uniform. You're not going to get the exact same composition of everything in each bowl. But of course, if you wanted to separate a soup, you could pull out all the pieces of chicken and vegetable and separate it out. So that's what makes that a heterogeneous mixture. Okay, so next, chemical changes. What can they be identified by? We talked about this in class, and there are 5 big clues that a chemical change has taken place. I'll give you a second to think about them. You can pause the video. Okay, so the first big one is that there's going to be a change in temperature, or there can be a change in temperature, I should say. Look. So it can get colder, but usually it'll get hot. We'll get into different types of reactions, ones that can get cold and ones that can get hot. We'll go into thermodynamics later. Super fun. I like it. So change in temperature, so you mix 2 reactants together and then you go and you grab the flask. Don't do that, by the way. This is completely hypothetical. Don't burn yourself. Never touch anything. Hot and cold glassware look exactly the same. But like if you were to hold it, you can feel the temperature rising. A good example of this is like those hand warmer things. You take them out of the package and you like knead them and then they start getting hot. If you like go to hockey games or something, you're probably pretty familiar with them because everyone uses them. And that's a chemical reaction going on inside of that little pouch that's causing it to heat up. or even like those like Thermacare patches that you can put on your back or shoulders or whatever. That's a chemical reaction going on in those pouches that's causing it to heat up. So another sign of a chemical change is the formation of a precipitate. And what this means is you're taking two aqueous solutions, so a solution, something dissolved in water, and you're mixing them together, and then a solid forms. It's like a powder, it falls down, hangs out at the bottom. That's a precipitate. So it's the formation of a solid. But use the word precipitate because that's the correct word. Another example is, or another sign is odor. The smell changes, it gets weird, it gets gross. That happens. There's a lot of compounds that smell pretty bad, and when you mix it with something else, it starts smelling even worse. So an odor is produced. Another thing is color change. If it goes from, so later on, you'll do titration labs, which is acid-base reactions, and it's super fun. And you're going to figure out when it's changed because it'll change color. And it's kind of tricky to get the right color, but it's so much fun, and it's like my favorite lab ever. And the last one is formation of a gas. And this one typically goes with the change in temperature. Typically, you get a gas when something is getting hotter. Not always, but usually. So formation of a gas. So you start seeing bubbles, bubbling, that's a big sign. Okay. Contrast extensive and intensive properties and give an example of each. So what does it mean for a property to be extensive? Basically, it means that it is dependent on the amount of substance present. And a good example of this is going to be mass. So mass is the amount of matter in an object. So if you have more of the object, the mass is going to be higher. And then intensive is independent of amount present. And go ahead and think for a second while I do this. What's a property we've talked about quite a bit in class? We spent probably like 20 minutes going over it. That's intensive. What is that? So I'm going ahead and highlighting because this is how I've always remembered it. Words are like how I remember things. So intensive is independent. So the property that we've talked about a lot that's intensive is density. It doesn't matter if you have like a small gold nugget or a giant like bar of gold. The density is the exact same for both. Okay. Number 9, in chemistry, all recorded measurements must have 3 things. What are they? So the first thing is really simple. Don't overthink it. You have to have a number. If you're going to have a recorded measurement, you have to write down a number. So a number. And what else do you have to have? What needs to follow the number? A unit of measurement. I'm sure everyone has heard at some point, you can't have a naked number, and it's still true. It's still true here. So the third thing that we have to have that we talked about that people kind of don't really like, but it exists, it's a thing we have to deal with, is significant figures. significant figures. Okay, number 10. What are the SI units of measurement for temperature and volume? So for temperature, the SI unit is Kelvin. Kelvin, and it's represented with a capital K. For volume, it is cubic meters. Typically, we tend to work in cubic centimeters, so it's like a derivative of the SI unit, but that's cubic centimeters is not it. Okay. So number 11 lists the significant figure rule. So this part is super important. Significant figures are always going to follow you, like everywhere you go, any type of chemistry class you take, it's there. So definitely keep these in mind, remember these, study these rules hard. Okay, so the first rule is that all non-zero numbers are significant. And what I mean by this is literally just any number that's not a zero. So if I have that number, all of those are significant. I have 4 significant figures there. So next is zeros sandwiched between 2 non-zero numbers are significant. And what I mean by this is if I have the number 808, that has 3 significant figures. That's a captive 0, so it counts as significant. The third rule is that leading zeros are not significant, even if there's a decimal. I know a lot of people, they see a decimal and they start counting all of those zeros as significant. So if we have the number 089693, sorry, that's 3 significant figures because that trailing 0 doesn't count. And in the same way, if I have 00 point, that number only has 2 significant figures. Even though that decimal is there, all of those zeros behind it are still leading, so they don't count. Okay, so the last one is that trailing zeros in a number with a decimal are significant. So if there is no decimal, those trailing zeros are not significant. So if I have like that, that's 2 significant figures because there's no decimal. But if the second I put a decimal there, that's 3. And if I add another 0, that's 4 significant figures. Yes. So number 12, find the density of a cube with a mass of 15.5 grams and a volume of 7.8 cubic centimeters. Okay, so I'm going to go ahead and switch to a whiteboard for this. Okay, so, oh shoot, I have to pull up the worksheet. Okay, so what is the formula for density? So the formula is, right, can I draw? Okay, The formula is D equals mass over volume. And in this case, it's going to be grams over cubic centimeters. That's what it typically is, but that can vary depending on the question. So we have our mass is 15.5 grams divided by 7.8 cubic centimeters. So one thing about Miss Adams, you have to write your units, you have to write the formula. If you don't, you will get points docked. And basically from here, it's just a math problem. We're gonna divide and we're gonna get our answer. But I want you to go ahead and think about, look at this problem. How many significant figures should your answer have? Pause the video, think about it. Gotta learn how to determine these things. So since we're doing division, we're basing this off of the fewest significant figures given. Both of these numbers were given to us. Neither of them are a conversion factor. So this has 2 sig figs and this has 3. So 2 is fewer, so our answer needs to have 2 sig figs. And once you divide, it should be something like 1.98, which is 3. But if you round up, you just get 2, right? But 2 is just 1 significant figure. We need 2. So what we're going to do is we're going to put 2, a decimal, and then a 0. And now we have 2 significant figures. So 2.0 grams per cubic centimeter. And that's your answer. Okay. Now we're going to how can I go back? Okay, sorry, I struggled a little there with that. So next up is question number 13. So my door frame is 167.8 centimeters across. How many inches of molding do I need to buy to frame my door, the top of the door? So we have 1.67, that's wrong. Okay, so we have 167.8 centimeters. So there's a conversion factor that she went over in class that you have to remember for this. It's centimeters to inches. So go ahead and pause, think about it, and then play again when you remember it or you think you have it. So it's 2.54 centimeters is equal to 1 inch. So now we're going to do some dimensional analysis. I'm going to go 167.8 centimeters. And I do mine like this. So we have centimeters on top, so it has to be on bottom. Centimeters. So we're going to put our conversion factor 2.54 centimeters down here and 1 inch on top, and that's it. So we're going to cross out our units because you will dock points if you don't, and do some math, and you're going to come up with your answer. So here's the question. How many significant figures does your answer need to have in this problem? So your answer needs to have 4. It's easy to just look at this dimensional analysis problem, see that 2.54 and say 3. And that's totally an understandable mistake to make. So if you did that, that's fine. That's cool. You're learning. So when we're determining significant figures, we always go based on what's given in the problem, never conversion factors, never numbers that we pull from other sources. So we have 4 significant figures. and you should get 66.06 inches. And that's your answer. And that's it. That's all I have for this this first session. So if I said anything or did anything you don't quite get it, go ahead and shoot me an email, text me over the remind, and I'll do my best to respond within like 24 hours. So hopefully I will see you guys on Wednesday.